Hi, my name is Jayme Zesiger,
And my name is Jane Eichwald.
and today we will be discussing orientation selective synthesis and evaluation of platelet aggregation inhibitory activity of lactam carboxamides. Nitrogen-containing molecules like these dominate the field of medicinal chemistry because of their therapeutic potential, and they're often naturally occurring. Currently, more than 75% of FDA-approved drugs include nitrogen-containing heterocyclic motifs. In addition to that, nitrogen-containing compounds represent around 20% of the total number of compounds that have demonstrated a cardiovascular effect. Lactam carboxamides are cyclic amides that bear a primary amide side group and have the potential to be useful in pharmaceuticals due to the observed antithrombotic activity in mice models. As this is a progress report, we will discuss the compounds we have already successfully synthesized, as well as how we are able to use data to identify the structures of our compounds.
Heart attack and stroke are among the most common causes of death worldwide, and they are mostly caused by significant blood clotting in the arteries. This is a condition known as arterial thrombosis. Antithrombotic drugs are commonly prescribed in medical settings to prevent blood clot formation through inhibition of platelet aggregation, inhibition of fibrin strands, and the ability to dissolve existing clots. As Jayme mentioned above, lactam carboxamides have been shown to minimize blood clotting, but it is significant to note that the observations have found them to be more effective than prescribed drugs such as aspirin. In vitro studies indicate that collagen plays a role in the aggregation of platelets and initiation of clotting activity at the site of an injury. Exploration into inhibitors in this process, however, is limited, as we are currently only aware of a few small molecule inhibitors. The mechanism in which they inhibit and affect certain protein-protein interactions is unknown and still under investigation. Funding and research focused on the development of applicable therapeutics and prevention strategies for cardiovascular diseases is insufficient, and the reason why we were motivated to further explore the field.
Research so far has been focused on four-membered groups such as penicillin and cephalosporin, which are both beta-lactams well known for their use in antibiotics. Possible reasons for the lack of research into use of lactam carboxamides could be due to the challenges posed during formation of the molecule. Compounds that contain 3, 4, 7, 8, and 9-membered rings show a significant amount of ring strain, especially 3 and 4-membered rings, whose ring strain has been measured to be 27.7 and 26.3 kilocals per mole respectively. These values represent that they are the most susceptible to ring opening. The mechanism of nucleophilic substitution as a way to create the lactam carboxamide has been the main focus of current research. In some cases, a coupling agent such as dicyclohexylcarbodiimide, or DCC, is used, such as the example above, in order to form a good leaving group. These coupling agents are not cost-effective, and they pose certain hazards as they are both irritants, highly flammable, and produce waste that is difficult to dispose of. Lactam carboxamides have also been formed using moisture-sensitive acid chlorides, or anhydrides. These reagents are difficult to obtain as there is a limited stability and shelf life of their reagents. The preparation of these reagents is also very hazardous as they are corrosive in nature.
Our goal was to design efficient, cost-effective, sustainable, and modular strategies for accessing nitrogen-bearing cyclic compounds. We wanted to expand upon the halolactone, which was previously synthesized by Morgan Rodriguez, a former member of our research group. Under the previous work section in Figure 2, you can see that in order to form the 2-oxopiperidine, or compound number 1, we reacted an anhydride with an azodiene in a Castagnoli-Cushman reaction. Our proposal discussed the method above to be applied to rings of various sizes as shown by the symbol N in compound number 1 of Figure 2. However, in practice, we chose to focus on 5-membered rings in order to first test our methodology using simpler and more stable rings. We thought this would be an effective and efficient way to create our compounds and evaluate our approach before pushing the limits and expanding to rings of different sizes. Under Figure 2, you can see our proposed plan, which N-bromosuccinimide, or NBS, and dichloromethane, or DCM, were used in the halolactonization of the 2-oxopiperidine to form the halolactone. NBS is used to give the electrophilic bromine essential to the formation of the epoxide. From there, we explored the possibility of an amine-induced ring opening reaction of the halolactone. This in turn leads to the formation of compound number 3, the desired Lactam carboxamide. This mechanism involves the attack of the carbonyl carbon on compound number 2 by an amine inducing ring opening. The subsequent addition of a base leads to an intramolecular SN2 reaction that forms the epoxide.
Now we can discuss our results. Our reaction proceeded based on its regioselectivity, as was noted in the formation of the epoxide, and it was stereospecific due to the preference of the 6-endo product over the 5-exo product, which was due to the fact that our carbon-carbon double bond is terminally substituted by a carbocation stabilizing group, the aryl group. Going back to our mechanism, we know that the reaction is taking place through the attack of the carbonyl carbon rather than attacking the bromine group through an SN2 reaction. This is due to the fact that the reaction utilized a secondary amine. If the SN2 reaction had taken place, the secondary amine would have replaced the bromine group and we would have been unable to open up the lactone. Compounds 3A through 3G down below were successfully synthesized and represent the different possibilities offered by adding different motifs to the R group on compound 1. Figures 3 through 5 show the spectroscopy data of compound 3E, where the aryl group is replaced by a paramethoxyphenol, or PMP group. The techniques we used to determine the structure of our compounds were HNMR, CNMR, and depth 135, as seen in figures 3 through 5. HNMR is used to detect the number of protons in a molecule. On the other hand, CNMR is used to detect the number of different carbons or sets of equivalent carbons that are in a molecule. And depth 135 is used to detect CH-containing carbons. A carbon bearing a hydrogen will show up. It also gives directionality to distinguish between CH2s, seen as pointing down, and CH or CH3 bonds seen pointing up.
Using these forms of spectroscopy, we were able to determine what compounds were formed from our reactions, as you can see listed in the results section. We are excited to take these results and expand them with compounds larger than 5-membered rings. We would like to thank Central Washington University and the Chemistry Department for making this possible, as well as the Office of Undergraduate Research for funding our research. A big thank you to Dr. Beng for being our mentor and guiding us through this, and thank you to the Beng Group.